There's a place in the cosmos where the rules of physics, as we know them, simply break. Picture this, a realm where light doesn't travel in straight lines but spirals helplessly, trapped in an invisible vortex. Where gravity doesn't just pull, it warps, twists, and shreds the very fabric of space and time. These are the universe's most unstable zones, the chaotic frontiers where light and gravity collide in a never-ending dance of destruction and creation. And what happens here doesn't just stay here, it shapes everything we see, from the birth of galaxies to the fate of stars. Think about the most violent storm you've ever witnessed. Now multiply that by 1 billion, and you might come close to the fury of a black hole's event horizon or the cataclysmic crash of 2 neutron stars. These aren't just abstract ideas from a textbook, they're real, raging phenomena that push the limits of what's possible. And yet, hidden within their chaos are clues to the universe's deepest secrets: how matter forms, how time behaves under extreme pressure, even how reality itself might be structured. It's as if the cosmos has built these unstable zones as cosmic laboratories, testing the laws of physics in ways we're only beginning to understand. So why should we care about these distant, violent corners of space? Because they're not as far removed from us as they seem. The same forces that create a black hole's crushing grip also shaped the atoms in your body. The light struggling to escape these cosmic battlegrounds carries stories from the dawn of time. This isn't just a journey through space, it's a journey through the very building blocks of existence. And by the end of this video, you'll see the universe differently, not as a static backdrop, but as a dynamic, ever-changing arena where light and gravity are locked in an epic struggle, one that's happening all around us in ways both visible and invisible. The adventure starts here at the edge of understanding, where every discovery raises new questions, and every answer leads us deeper into the mystery. The moment you step into one of these cosmic war zones, the familiar laws of physics start bending under pressure. Take a black hole's event horizon, the point of no return where gravity wins its ultimate victory over light. Here, space-time isn't just curved, it's funneled into an inescapable spiral like water draining from a bathtub. But it's not just black holes that twist the rules. Neutron stars, the dense corpses of dead suns, pack more mass than our entire solar system into a city-sized space. Their gravity is so intense that a sugar cube-sized chunk would weigh as much as a mountain on Earth. And when 2 of these stellar zombies collide, the explosion ripples space-time itself, sending out gravitational waves we can detect from billions of light years away. What makes these regions truly unstable isn't just their raw power. It's how they distort the very tools we use to study them. Light, our cosmic messenger, gets stretched, squeezed, and even split apart. Near a black hole, photons can orbit endlessly in a ghostly halo before either escaping or vanishing forever. Meanwhile, matter doesn't just fall in, it's shredded into superheated plasma, spinning at nearly the speed of light like water circling a drain. These aren't just abstract theories. Telescopes have captured quasars, the blazing hearts of distant galaxies, where entire rivers of gas spiral into oblivion, glowing brighter than 1 trillion stars. Yet within this chaos lies a strange order. These extreme environments are nature's way of stress-testing Einstein's equations. When 2 black holes merge, the energy they release in gravitational waves briefly outshines every star in the observable universe combined. That energy isn't random, it follows precise mathematical rhythms, like a cosmic drumbeat echoing the shape of spacetime itself. Even the way light bends around massive objects, a phenomenon called gravitational lensing, acts as a natural telescope, revealing galaxies too faint for our instruments to see unaided. So why does this matter to us here on our tiny blue planet? Because these unstable zones are cosmic alchemists. The gold in your jewelry, the uranium in nuclear reactors, even the calcium in your bones were forged in the violent deaths of massive stars or the collisions of neutron stars. We're literally made of stardust, recycled through these extreme environments. And every time astronomers detect a new gravitational wave or observe light bending around a distant galaxy, we're glimpsing the invisible machinery that shaped our universe. It's a reminder that the cosmos isn't just out there, it's in us, around us, and woven into the fabric of reality itself. Black holes don't just bend the rules, they rewrite them entirely. Picture a place where gravity becomes so overwhelming that even time itself slows to a crawl. If you were to hover near the event horizon, a mere observer watching from a safe distance would see your movements stretch into slow motion, your light redshifted into invisibility as you fade from view. But the real spectacle happens just beyond that invisible boundary. Matter doesn't just fall in quietly, it's ripped apart atom by atom, stretched into a searing hot stream of plasma called an accretion disk. This disk glows with the heat of a billion suns, a swirling maelstrom where particles collide at nearly the speed of light, generating bursts of X-rays and gamma rays that can be detected across the cosmos. And then there are quasars, the universe's ultimate powerhouses. These are supermassive black holes at the centers of galaxies, but they're anything but dormant. As they devour gas, dust, and even entire stars, they launch jets of energy thousands of light years into space, outshining every star in their host galaxy combined. It's a cosmic paradox, the darkest objects in existence, yet capable of producing the brightest beacons we've ever observed. These jets are so powerful they can carve out bubbles in intergalactic space, shaping the evolution of galaxies millions of light years away. But black holes aren't just destructive, they're also cosmic recyclers. Some of the matter spiraling toward oblivion doesn't actually cross the event horizon instead. It's hurled back out into space by immense magnetic fields and centrifugal force, seeding the universe with heavy elements and fresh material for new stars and planets. Even the gravitational waves they produce when colliding send ripples through spacetime, offering us a whole new way to observe the universe. What's truly mind-bending is how these gravitational titans challenge our understanding of reality. Near a black hole, space is so warped that you could theoretically see the back of your own headlight bend so severely it wraps around the void. And if you dared to cross the event horizon, the laws of physics as we know them would cease to apply. Time and space swap roles, turning what was once a one-way journey into an inevitable plunge toward the singularity, a point of infinite density where all known science breaks down. Yet for all their mystery, black holes are surprisingly common. Nearly every large galaxy harbors one at its core, including our own Milky Way, and they come in all sizes, from stellar mass black holes, born from the collapse of massive stars, to the supermassive behemoths weighing billions of times our sun's mass. Some even wander through space like cosmic nomads, invisible unless they happen to tug on a nearby star or cloud of gas. Studying these extreme environments isn't just about satisfying curiosity, it's about decoding the universe's deepest secrets. Black holes are the ultimate laboratories for testing the limits of gravity, quantum mechanics, and even the nature of information itself. Every flicker of light, every ripple in space-time, carries clues about how the cosmos operates under conditions we could never recreate on Earth. And with each discovery, we're not just learning about black holes, we're uncovering the hidden rules that govern everything from the smallest particles to the largest structures in existence. Neutron star collisions are cosmic car crashes on a scale we can barely comprehend. Imagine taking two city-sized objects, each with more mass than our Sun, and smashing them together at nearly half the speed of light. The shockwave from this impact doesn't just ripple through space, it warps the very fabric of spacetime itself, sending out gravitational waves we can detect from billions of light years away. But the real spectacle happens in the wreckage. As the neutron stars spiral toward each other, their immense gravity stretches and shreds them, creating a swirling vortex of superheated debris. In less time than it takes to blink, this cosmic furnace forges elements heavier than iron, gold, platinum, uranium, flinging them out into the universe in a dazzling explosion called a kilonova. What makes these collisions so extraordinary isn't just their violence, it's how they reveal the hidden alchemy of the cosmos. Every gold ring or platinum necklace on Earth likely owes its existence to a neutron star merger that happened eons ago. These events are the universe's ultimate foundries, operating under conditions so extreme that atomic nuclei are crushed together with enough force to create elements that don't form in regular stars. And the aftermath is just as mind-bending. The kilonova's brief but brilliant flash can outshine an entire galaxy, lighting up the surrounding space with a cocktail of radioactive decay and high-energy radiation. But here's where things get even stranger. The collision doesn't just produce heavy elements, it creates conditions so unstable that even light struggles to escape. The debris forms a rapidly spinning, ultra-dense blob known as a hypermassive neutron star, which might only last milliseconds before collapsing into a black hole. During that fleeting moment, the star's magnetic field becomes trillions of times stronger than Earth's, launching jets of particles at near light speed. These jets are so energetic they produce gamma-ray bursts, some of the most luminous events in the universe visible across cosmic distances. Scientists first confirmed this spectacular process in 2017, when gravitational wave observatories detected ripples from a neutron star collision while telescopes simultaneously caught the kilonova's glow. It was like witnessing a cosmic symphony in multiple dimensions, one where gravity, light, and nuclear physics all played interconnected roles. Since then, each new observation has peeled back another layer of mystery, showing how these collisions shape the distribution of elements across galaxies and even influence where new stars can form. What's truly humbling is realizing that these cataclysms aren't rare anomalies, they're part of the universe's life cycle. Neutron star mergers might happen multiple times a year in any given galaxy, meaning the very atoms that make up our world were born in chaos. Every time we study one of these events, we're glimpsing the unpredictable, unstable zones where the cosmos reinvents itself, and where the seeds of planets, life, and even future stars are forged in fire. Quasar jets are the universe's ultimate particle accelerators, operating on a scale that dwarfs anything humanity could ever build. Picture a supermassive black hole, millions to billions of times heavier than our Sun, devouring everything that strays too close. But not all that material disappears forever. Some of it gets funneled into twin beams of plasma, launched outward at nearly the speed of light. These jets punch through entire galaxies, stretching for distances so vast they could bridge the gap between Earth and the nearest stars thousands of times over. What keeps these jets so tightly focused over such enormous distances? The secret lies in a cosmic balancing act between gravity and magnetic fields. As matter spirals toward the black hole, it forms a swirling disk of superheated gas and dust. The rotation of this disk, combined with the black hole's spin, twists magnetic fields into tightly wound coils like cosmic springs under unimaginable tension. When these springs snap, they fling particles outward in a focused beam, channeling their energy with precision that defies intuition. Inside these jets, particles don't just move fast, they reach energies so extreme they make Earth's most powerful particle colliders look like toys. Electrons and protons get whipped up to velocities just a hair's breadth below light speed, colliding with enough force to produce gamma rays and X-rays detectable across the universe. These are the same high-energy particles that create the glowing halos around quasars, visible from billions of light-years away. But the most fascinating part: these jets aren't just chaotic streams of destruction, they're sculptors. As they plow through galaxies and intergalactic space, they carve out vast bubbles in the surrounding gas, heating it up and preventing it from cooling into new stars. In some cases, they can even trigger star formation by compressing nearby gas clouds, like a cosmic domino effect. We've seen evidence of this interplay in galaxies like M87, where the black hole's jet stretches for thousands of light years, bending under its own momentum and lighting up the surrounding space. Even more astonishing, some jets show structures within them, knots and shockwaves that suggest they're not just smooth streams but dynamic, ever-changing rivers of energy. Understanding these jets isn't just about mapping the extremes of physics, it's about decoding how black holes shape their surroundings. They're proof that even in the most unstable zones of the universe, there's an underlying order, a set of rules that govern how matter, light, and energy interact under conditions we can barely imagine. And with every new observation, we're peeling back another layer of this cosmic mystery, inching closer to understanding how these titanic forces built the universe we see today. Gamma-ray bursts are the universe's ultimate fireworks brief, blinding flashes of energy so intense they outshine entire galaxies. In just a few seconds, one of these explosions can release more power than our Sun will emit over its entire 10 billion-year lifespan. But unlike fireworks, these aren't just pretty lights. They're cosmic disasters born from the deaths of massive stars or the catastrophic mergers of neutron stars, where matter is torn apart in a storm of radiation. What makes these bursts so staggeringly powerful? It starts with a star at least 30 times heavier than our Sun. When such a star runs out of fuel, its core collapses into a black hole or neutron star in seconds. But the outer layers don't just fall quietly. They rebound in a shockwave so violent it launches jets of plasma at nearly the speed of light. These jets, focused into narrow beams by intense magnetic fields, pierce through the dying star like a cosmic blowtorch. The moment they break free, they unleash a torrent of gamma rays, the most energetic form of light visible across billions of light years. Yet the real mystery lies in what happens next. Even after the initial burst fades, the afterglow lingers for days or weeks, radiating X-rays, visible light, and radio waves. This fading echo isn't just debris, it's a cosmic fingerprint, revealing the environment where the explosion occurred. Some bursts show signatures of dense gas, suggesting they came from star-forming regions, while others appear in emptier space, hinting at mergers between neutron stars. But here's where things get even stranger. Some gamma-ray bursts last less than 2 seconds, while others linger for minutes. The short ones likely come from neutron star collisions, where the violence is concentrated and sudden. The longer bursts, though, seem tied to the collapse of especially massive stars, where the black hole's birth creates a sustained energy release. And then there are the outliers, bursts so energetic they defy current models, as if the universe is showing us physics we haven't even dreamed of yet. Detecting these bursts is like catching lightning in a bottle. Satellites like NASA Swift and Fermi scan the skies around the clock, waiting for the telltale flash of gamma rays. When one is spotted, telescopes worldwide swing into action, racing to capture the afterglow before it fades. These observations have revealed bursts from the edge of the observable universe, some dating back to when the cosmos was just a fraction of its current age. Why does this matter? Because gamma-ray bursts aren't just distant curiosities, they're cosmic probes. The light from these explosions travels through galaxies, gas clouds, and the vast voids between them, picking up clues about the universe's structure along the way. They might even hold answers to fundamental questions, like how heavy elements spread through space or whether the speed of light has changed over billions of years. And then there's the unsettling possibility that a burst could happen closer to home. A nearby gamma-ray burst pointed directly at Earth could strip away our ozone layer, triggering mass extinctions. It's a reminder that the universe isn't just awe-inspiring. It's unpredictable, capable of unleashing forces beyond our control. Yet even this danger underscores why studying these explosions matters. By unraveling their secrets, we're not just exploring the cosmos, we're learning how to read its warnings, written in light older than our planet itself. Accretion disks are nature's most violent carousels, spinning storms of superheated gas where gravity and chaos dance on a razor's edge. Imagine taking all the energy of a raging wildfire and compressing it into a swirling disk no wider than our solar system, where temperatures soar to millions of degrees and particles whip around at nearly the speed of light. This isn't science fiction, it's the reality around black holes and neutron stars, where matter doesn't just fall in quietly, it's shredded, heated, and twisted into a luminous vortex that defies intuition. At the heart of these disks lies a paradox. The closer matter gets to the black hole, the faster it spins, like water circling a drain. But unlike a bathtub, there's no smooth flow here. Friction between gas particles generates so much heat that the disk glows white-hot, emitting X-rays and gamma rays powerful enough to sterilize planets light years away. Yet even as matter spirals inward, not all of it meets its doom. Some gets caught in magnetic tornadoes, flung outward in jets that scream across space at 99% the speed of light. These jets aren't just side effects, they're cosmic blowtorches capable of shaping entire galaxies. What makes accretion disks so unstable isn't just their speed or heat, it's the way they constantly rewrite the rules. Magnetic fields twist into knots, creating turbulence that can fling matter inward or outward without warning. Gravity fights centrifugal force in a tug of war, while radiation pressure tries to blow the disk apart. It's a battlefield where no single force ever wins for long, producing flickers and flares that astronomers detect as sudden bursts of energy. Some disks even pulse rhythmically like cosmic heartbeats, revealing the hidden structure beneath the chaos. But these whirlpools of doom aren't just destructive, they're also creative. The same processes that tear matter apart also forge heavy elements and launch them into space, seeding the universe with the building blocks of planets and life. And by studying their light, we've uncovered clues about how black holes grow. The flickering patterns in an accretion disk's glow act like a cosmic barcode, revealing the mass and spin of the monster at its center. Some disks even show gaps, clean rings where newborn planets might be forming, defying the odds in this hostile environment. The most fascinating disks orbit supermassive black holes where the scale becomes almost incomprehensible. In galaxies like M87, the disk spans distances so vast it could swallow our solar system 1,000 times over, yet it rotates with eerie precision, like a gargantuan vinyl record playing the universe's most extreme soundtrack. And when two black holes merge, their disks flare up in a spectacular light show, sending ripples through space-time and glowing brighter than 1 trillion stars. Understanding these cosmic whirlpools isn't just about mapping the extremes, it's about decoding how the universe grows and changes. They're the engines behind quasars, the power sources for gamma-ray bursts, and the sculptors of galactic landscapes. Every flicker, every jet, every turbulent eddy holds a piece of the puzzle, revealing how chaos and order collide in the most unstable zones of existence. And with each new discovery, we're not just observing these maelstroms, we're learning the language they speak, written in light, gravity, and fire. Dark matter is the universe's silent architect, shaping chaos without ever revealing itself. While we can't see it, touch it, or even detect it directly, its gravitational fingerprints are everywhere, especially in the most unstable corners of the cosmos. Picture a spiderweb stretching across billions of light years, its threads made of dark matter, pulling galaxies into clusters and sculpting the voids between them. This cosmic web isn't just background scenery, it's the scaffolding that holds the universe together, and where its threads knot tightly, chaos thrives. Take galaxy clusters, the universe's most massive structures. When these titans collide, dark matter's gravity becomes a wrecking ball. The Bullet Cluster, a famous example, shows two galaxy clusters smashing through each other like ghosts passing in the night. The visible gas, hot and bright, slams together and slows down, but the dark matter, unaffected by anything but gravity, sails right through, leaving its gravitational signature imprinted on the background light. This is gravitational lensing at its most extreme. Dark matter's invisible hand bending starlight into arcs and rings, revealing where the true mass lies. But dark matter's influence doesn't stop there. Around black holes and neutron stars, where gravity runs wild, dark matter might be the unseen puppet master. Some theories suggest it could gather in dense halos around these objects, amplifying their gravitational pull or even feeding them like invisible fuel. Imagine a black hole not just devouring stars and gas, but also drawing in streams of dark matter, its presence subtly altering how the accretion disk flickers or how jets launch into space. We've even detected galaxies that seem to rotate too fast for the visible matter they contain, hinting that dark matter's grip might be steering stars into unstable orbits, setting the stage for cosmic collisions. The most tantalizing clue: anomalies in gravitational wave signals. When black holes or neutron stars merge, the ripples in spacetime sometimes carry unexpected echoes or timing quirks. Could these be traces of dark matter's influence, warping the environment around the collision? It's a frontier of research so cutting-edge that every new observation could rewrite the rules. What's clear is that dark matter doesn't just lurk in the shadows. It actively molds the universe's most violent landscapes, from twisting light around galaxy clusters to potentially fueling the engines of black holes. It's the hidden variable in every cosmic equation. And as we peer deeper into these unstable zones, we're not just searching for dark matter, we're decoding the invisible blueprint of reality itself. White holes are the universe's ultimate cosmic contradiction. Where black holes pull everything in, white holes would blast everything out. Imagine a singularity that refuses to swallow even a single atom, instead violently ejecting matter and energy into space like a cosmic fire hose with no off switch. This isn't just science fiction, it's a serious mathematical prediction emerging from Einstein's equations of general relativity. While black holes trap light behind an event horizon, white holes would theoretically have an event horizon that nothing can cross inward, only outward. They're the universe's one-way exit doors, spewing material with such force that approaching them would be like trying to swim up a waterfall at the speed of light. But here's where it gets even stranger. Some physicists speculate white holes could be the other end of black holes, connected by wormholes, tunnels through space-time that could, in theory, allow matter to traverse vast distances instantly. Picture a black hole in one corner of the galaxy sucking in a star, while somewhere else, a white hole convulses, expelling that same star's energy in a burst of radiation. It's a cosmic recycling plant on a scale so grand it defies imagination. The problem, we've never seen one. White holes remain purely hypothetical, with no observational evidence to confirm their existence. But that hasn't stopped scientists from exploring the idea. Some theories suggest white holes could explain certain ultra-high-energy cosmic rays, mysterious particles that hit Earth's atmosphere with more energy than anything our largest particle accelerators can produce. Others speculate that the Big Bang itself might have been a white hole event, a single point of infinite density suddenly erupting into the universe we know today. Even stranger is the question of how a white hole could form in the first place. Black holes are born from collapsing stars, but white holes would require time-reversed physics, as if a black hole's death played backward. Some models propose they could emerge from quantum fluctuations in spacetime, popping into existence like bubbles in a boiling cosmic soup before vanishing just as quickly. The search for white holes isn't just about finding exotic objects, it's about testing the limits of physics itself. If they exist, they could rewrite our understanding of gravity, quantum mechanics, and the very nature of time. Until then, they remain one of the universe's most tantalizing what-ifs, a reminder that even in the most unstable zones of reality, the cosmos still has surprises waiting in the shadows. Magnetars are neutron stars with a terrifying upgrade, nature's ultimate electromagnets, wielding forces so strong they could strip the data from every credit card on Earth from halfway across the solar system. These cosmic powerhouses are born from the same stellar explosions that create ordinary neutron stars, but with one critical difference: their magnetic fields are off the charts. Imagine taking Earth's magnetic field and cranking it up by a quadrillion times. That's the level of intensity we're talking about. At such strengths, the laws of physics as we know them start to warp. Atoms stretch into needle-thin shapes, and electrons are forced into bizarre spirals, unable to maintain their usual orbits. What makes magnetars truly unstable isn't just their raw power, it's how unpredictably they unleash it. Unlike black holes which steadily devour matter, magnetars can erupt without warning. When their crusts crack under immense pressure, events called starquakes, they release bursts of energy so violent they briefly outshine entire galaxies. In 2004, a magnetar 50,000 light-years away let loose a flare so powerful it temporarily ionized Earth's upper atmosphere, despite being far beyond our galactic neighborhood. But the real danger lies in their magnetic fields. These aren't just static forces, they twist and writhe like living things, creating loops and kinks that snap with the energy of a million nuclear bombs. When these magnetic lines rupture, they accelerate particles to near light speeds, generating deadly X-ray and gamma-ray flares. Some theorize that a magnetar flare within 10 light-years of Earth could trigger mass extinctions by shredding our ozone layer. Yet for all their destructive potential, magnetars are also cosmic goldmines for science. Their extreme conditions act as natural laboratories, letting us study matter under pressures and magnetic fields impossible to replicate on Earth. Some researchers even suspect they might be the source of fast radio bursts, those mysterious, millisecond-long blips of radio waves that have puzzled astronomers for years. The most fascinating part: magnetars don't last forever. Their monstrous magnetic fields gradually decay, and within 10,000 years, a blink in cosmic time, they fade into ordinary neutron stars. That means every magnetar we detect is a fleeting glimpse into one of the universe's most volatile phases, a reminder that even in the vastness of space, some forces are too intense to endure for long. Cosmic strings are like invisible scars left over from the universe's earliest moments' flaws, frozen into the fabric of reality when the cosmos was still a seething, newborn expanse. Picture a crack in ice, but instead of water, it's space-time itself that's fractured, forming filaments thinner than an atom yet denser than a mountain range. These aren't just theoretical oddities, they're potential time capsules from the first trillionth of a second after the Big Bang, when the universe underwent violent phase transitions, like water freezing into ice but on a cosmic scale. And if they exist, their influence could be written across the entire sky. What makes cosmic strings so bizarre is how they warp the rules of physics. A single string stretching across light years would carry enough mass to bend spacetime around it like a funhouse mirror. Light passing near one wouldn't just curve, it could split into double images, a phenomenon called gravitational lensing, but with a twist. Unlike black holes or galaxies, which distort light symmetrically, a cosmic string would create sharp, knife-edge deflections. Imagine looking at a star and seeing its ghostly twin hovering beside it, separated by a hair's breadth in the sky. That's the kind of space-time contortion these relics could produce, but the real chaos begins when strings interact. If two cosmic strings crossed paths, they might snap and reconnect, sending out ripples in space-time so powerful they dwarf the gravitational waves from colliding black holes. These vibrations could even birth particles out of pure energy, sparking fleeting bursts of radiation. Some theories suggest such events might leave imprints in the cosmic microwave background, the afterglow of the Big Bang, like faint fingerprints on an ancient canvas. Astronomers have already spotted curious temperature variations in this primordial light, and while other explanations exist, cosmic strings remain a tantalizing possibility. The most mind-bending part, these structures could be time travelers of a sort. According to certain models, a loop of cosmic string moving at near light speed might create closed time-like curves, regions where space-time loops back on itself, theoretically allowing for time travel. While this remains speculative, it underscores how these hypothetical defects could challenge our understanding of causality itself. Yet for all their potential impact, cosmic strings are ghosts in the machine, elusive, invisible, and so far undetected. Their existence hinges on theories that go beyond the standard model of physics, like certain versions of string theory or grand unified theories. If we ever found one, it wouldn't just confirm these ideas, it'd open a window into the universe's most volatile infancy, showing us how space-time itself crystallized from the chaos of creation. Until then, they remain one of cosmology's greatest what-ifs, a reminder that the universe's most unstable zones might not just be places, but ancient defects woven into the very fabric of reality. Beneath the apparent smoothness of space-time lies a hidden chaos, a seething, bubbling ocean of quantum foam. At scales a trillion times smaller than an atom, space itself may not be the calm, continuous fabric Einstein envisioned. Instead, it could resemble a stormy sea, with virtual particles popping in and out of existence, twisting the very geometry of reality into fleeting knots and whirlpools. This isn't just theoretical speculation. It's a frontier where the laws of quantum mechanics and general relativity collide, producing effects so bizarre they defy everyday intuition. Nowhere is this quantum turbulence more extreme than near black hole singularities. Here, gravity's crushing force amplifies the foam's instability, stretching space-time into microscopic wormholes that flicker into existence for mere fractions of a second. Some theories suggest these tiny tunnels could link distant parts of the universe, or even different universes before collapsing under their own instability. It's as if space-time itself is constantly rewiring its circuitry, creating shortcuts and dead ends in an invisible labyrinth. But the real shocker, these quantum fluctuations might not just warp space, they could alter the speed of light itself. In the froth of quantum foam, photons traveling through this chaotic landscape might encounter slight delays or detours, as if light were navigating an obstacle course at the smallest scales. Over vast cosmic distances, these tiny hiccups could add up, potentially explaining why some high-energy particles arrive at Earth slightly out of sync with expectations. What makes quantum foam so revolutionary is how it challenges our most fundamental assumptions. Einstein's relativity paints spacetime as a smooth stage where matter and energy perform. But at the quantum level, that stage becomes a dynamic, ever-changing entity, more like a boiling pot of water than a rigid grid. This tension between the large and the small is the heart of one of physics' greatest mysteries: how to reconcile gravity's cosmic dominance with quantum mechanics' subatomic rulebook. Some researchers believe the answer lies in the foam's turbulence. By studying how these quantum fluctuations behave near black holes or in the early universe, we might uncover clues to a unified theory of quantum gravity, a framework that would finally bridge the gap between the very big and the very small. Imagine a single set of equations that could describe everything from the orbit of planets to the spin of electrons, with quantum foam serving as the hidden thread tying it all together. Yet for all its promise, quantum foam remains frustratingly elusive. Its effects are so minuscule that current technology can't directly observe it. Some experiments, like ultra-precise atomic clocks or gravitational wave detectors, might one day catch whispers of its existence. Until then, this chaotic frontier remains a playground for theorists, a realm where the universe's most unstable zones reveal not just destruction, but the potential for a deeper, more unified understanding of reality itself. The implications stretch far beyond black holes. If spacetime is indeed foamy, it could reshape our ideas about information, entropy, even the arrow of time. Some models suggest quantum foam might preserve traces of events long after they've vanished from the macroscopic world, like cosmic fingerprints etched into the fabric of existence. Others propose it could hold the key to understanding dark energy, that mysterious force accelerating the universe's expansion. One thing's certain: in the quantum foam's turbulent depths, the universe is far stranger than we ever imagined. It's a reminder that even in emptiness there's endless activity, a hidden layer of chaos and creativity where the rules we take for granted are constantly being rewritten. And as we peer deeper into this submicroscopic storm, we're not just exploring space, we're decoding the very foundation of reality, one quantum fluctuation at a time. The universe has a strict rule: information never disappears. Every particle, every ripple of energy, every scrap of matter carries data about its history, a cosmic paper trail that, in theory, could be traced back to the dawn of time. But black holes laugh in the face of this rule. When matter crosses the event horizon, it's not just crushed into oblivion, it's stripped of its identity, its information seemingly erased from existence. This isn't just a minor glitch in the cosmic code. It's a full-blown paradox that pits quantum mechanics against general relativity in a battle for the soul of physics. At the heart of the conflict is Hawking radiation, the faint glow of particles that black holes slowly emit over eons. Stephen Hawking's groundbreaking work showed that black holes aren't eternal, they evaporate, leaving behind nothing. No trace of the stars, planets, or gas they devoured. This revelation sent shockwaves through the scientific community. If black holes vanish without a record, then the universe's ledger is incomplete, its most fundamental law broken. But what if the information isn't lost, just transformed? One radical idea suggests that every bit of data swallowed by a black hole gets imprinted onto its event horizon, like a cosmic fingerprint pressed into space-time itself. Imagine the surface of a black hole as a vast holographic hard drive, storing the quantum states of everything it consumes. As the black hole evaporates, this information could leak back out, encoded in the very Hawking radiation that once seemed to erase it. It's as if the universe has a failsafe, a way to preserve its secrets even in the most hostile environments. Then there's the firewall paradox, a twist so bizarre it sounds like science fiction. According to quantum theory, the event horizon should be an unremarkable boundary, a point of no return, but not a wall of fire. Yet some calculations suggest that to preserve information, the horizon might actually be a searing layer of high-energy particles, incinerating anything that crosses it. This would solve the paradox, but at a terrible cost. It would mean Einstein's vision of a smooth, continuous spacetime breaks down catastrophically at the black hole's edge. The stakes couldn't be higher. If information truly vanishes in black holes, then quantum mechanics, the framework underlying everything from atoms to smartphones, is fundamentally flawed. But if it survives, hidden in some exotic form, then our understanding of space-time, gravity, and even the nature of reality might need a complete overhaul. Recent breakthroughs in quantum gravity, like the discovery of islands inside black holes where information could hide, are pushing the debate into uncharted territory. What's emerging from this chaos is a startling possibility. Black holes might not be cosmic shredders after all. They could be the universe's most sophisticated encryption devices, scrambling information into forms we're only beginning to decipher. And the key to cracking their code might lie in the most unstable zones of all the quantum fluctuations at their cores, where the fabric of reality twists into knots we're still learning to untangle. Primordial black holes could be the universe's best-kept secret, tiny, ancient relics hiding in plain sight since the first chaotic moments after the Big Bang. Unlike the black holes we know today, born from collapsing stars, these would have formed when extreme density fluctuations in the infant universe created pockets of spacetime so warped they pinched off into singularities. Some might be as small as an atom weighing less than a paperclip. Others could rival mountains in mass, crammed into spaces narrower than a single proton. And if they exist, they'd be cosmic time capsules, preserving conditions from when the universe was less than a second old. The wildest part, these primordial black holes might not even behave like their modern counterparts. Because of their minuscule size, quantum effects would dominate their existence. The smallest ones could evaporate in a flash via Hawking radiation, exploding in bursts of energy equivalent to nuclear bombs. Others might linger, drifting through galaxies like invisible ghosts, occasionally colliding with stars or planets. Some theories even suggest they could be hiding in the cores of neutron stars, slowly devouring them from the inside out, a cosmic parasite undetectable until it's too late. But the real game changer is what these ancient objects could explain. If enough primordial black holes survived, they might account for dark matter, the invisible glue holding galaxies together. Unlike hypothetical dark matter particles, these would be real, tangible objects, just too small and dark to spot easily. There's even speculation that their collisions could produce the mysterious fast radio bursts that puzzle astronomers, or the odd high-energy cosmic rays that rain down on Earth with no clear source. Finding them, though, is like searching for needles in a universe-sized haystack. Their faint Hawking radiation would be drowned out by cosmic background noise, and their gravitational influence would be minuscule unless they passed absurdly close to us. But scientists aren't giving up. Some are scanning old neutron stars for signs of unexplained heating. a hint that a primordial black hole might be lurking inside. Others are watching for brief flashes of light as these tiny black holes pass in front of stars, bending their light in telltale ways. The stakes couldn't be higher. If we ever caught one, it wouldn't just be a new class of object, it'd be a direct portal to the universe's birth. The conditions that birthed them were so extreme they'd make black hole collisions look tame by comparison, offering a glimpse into physics we can't recreate in any lab. And if they are dark matter, that would rewrite our understanding of how galaxies form, how the cosmos evolved, and what truly fills the vast voids between stars. Until then, they remain one of the universe's most tantalizing what-ifs, proof that sometimes the smallest things can hold the biggest secrets. Gravitational waves are the universe's hidden language, a silent symphony written in the warping and stretching of spacetime itself. When two black holes spiral toward collision, they don't just crash, they send out tremors that ripple across the cosmos at the speed of light, distorting the very fabric of reality as they pass. These waves aren't just faint echoes, they're physical proof of Einstein's century-old prediction that space isn't a static stage but a dynamic, living entity that can bend, twist, and vibrate. And in 2015, when scientists first detected these ripples using LIGO, humanity gained an entirely new sense: the ability to hear the universe's most violent events, even in total darkness. What makes gravitational waves so revolutionary is how they reveal the invisible. Light can be blocked, absorbed, or scattered, but spacetime ripples pass through everything: galaxies, dust clouds, even other black holes carrying undisturbed information about their origins. A single chirp in the data can tell us the masses of colliding objects, how fast they were spinning, even the direction they faced when they merged. It's like listening to a cosmic fingerprint, where every oscillation holds clues about the chaos that created it. The most extreme events leave the loudest imprints. When neutron stars collide, their gravitational waves arrive as crescendos, followed by a telltale afterglow of light across every wavelength, a kilonova's fireworks display. Black hole mergers, though, are darker affairs. Without any light to accompany them, their waves are our only window into these invisible cataclysms, some so powerful they briefly outshine every star in the observable universe combined. And then there are the mysteries events like GW 1924-26, a ripple so peculiar it might have come from a black hole swallowing a neutron star, or something even stranger we haven't imagined yet. But gravitational waves do more than just announce cosmic disasters. They're reshaping our understanding of how the universe evolves. By mapping mergers across billions of years, we've discovered that black holes grow faster and more frequently than anyone predicted, hinting at unseen processes in galactic cores. Some waves even carry hints of extra dimensions or modifications to Einstein's gravity, subtle deviations that could point toward new physics. And as detectors grow more sensitive, we're starting to catch the background hum of countless distant mergers, a low-frequency chorus of spacetime itself vibrating with the footsteps of invisible giants. The future of this field is even more thrilling. Upcoming observatories like the space-based LISA mission will detect waves from supermassive black holes merging at the hearts of galaxies, events so colossal they shake spacetime for years. Others might catch the faint whispers of primordial black holes colliding, or even cosmic strings snapping if they exist. With every new detection, we're not just adding to a catalog of events, we're piecing together a hidden history of the universe, written in the language of gravity. And as we listen closer, we're bound to hear surprises, signals that defy explanation, opening new chapters in the story of where light and gravity collide. Dark energy isn't just stretching the universe, it's rewriting the rules of cosmic chaos. While gravity pulls matter together, this invisible force does the opposite. pushing space itself apart with a strength that grows over time. Picture a tug of war where one side keeps getting stronger, stretching the rope until it snaps. That's dark energy's grip on the cosmos, and its influence seeps into every unstable zone, from the orbits of colliding galaxies to the violent mergers of black holes. Take galaxy clusters, the universe's largest structures. Normally, gravity binds them tightly, but dark energy acts like an invisible tide, loosening their grasp. Over billions of years, it could pull galaxies apart faster than gravity can reel them back in, turning cosmic collisions once common into rare events. Even now, astronomers see hints of this, some clusters drifting eerily apart, their motions defying expectations. And when galaxies do collide in a dark energy-dominated era, the show might look different, slower, more drawn out, like a dance where the partners keep getting yanked farther apart. But the real drama unfolds around black holes. As dark energy accelerates the universe's expansion, it could strangle the flow of gas and stars feeding these gravitational monsters. A black hole starved of material might shrink over eons, its accretion disk flickering out like a dying campfire. Mergers between black holes, already cosmic rarities, could become even scarcer as the space between them stretches faster than gravity can bridge the gap. Some models suggest that in a far future universe, black holes might end up isolated, drifting alone in an ever-expanding void, the most unsettling possibility. The Big Rip, a scenario where dark energy's influence grows so dominant it overpowers even the forces holding atoms together. In this apocalyptic endgame, first galaxies, then stars, then planets would be torn apart, followed by molecules and finally atoms themselves. It's a fate so extreme it makes black holes look tame by comparison. While this remains speculative, observations of distant supernova and galaxy distributions suggest dark energy's strength is indeed constant or even increasing, leaving the question open. Is the cosmos destined for a slow fade or a violent shredding? Yet dark energy's role isn't purely destructive. Its repulsive force might also sculpt the universe's large-scale structure, creating vast voids where instability thrives in unexpected ways. In these near-empty regions, rare particles or exotic physics could dominate, offering clues to dark energy's true nature. Some theories even propose that it's not a constant force but a dynamic field, fluctuating in ways that could spawn new unstable zones we haven't yet imagined. Unraveling this mystery means peering into the most extreme environments. When telescopes catch a black hole merger billions of light-years away, they're also measuring how dark energy has stretched spacetime during the light's journey. Gravitational wave detectors like LISA could one day spot mergers in epochs when dark energy's influence was weaker, helping us map how its grip has changed over cosmic history. Each observation is a piece of the puzzle, revealing whether the universe's acceleration is a slow cruise toward cold emptiness or a countdown to a cataclysm. What's clear is that dark energy doesn't just shape the universe's fate, it's an active player in its most unstable arenas. From quietly starving black holes to potentially ripping reality apart, its influence whispers through every corner of the cosmos. And as we decode its secrets, we're not just learning about the universe's end. We're discovering how even the most violent cosmic dramas are staged on a canvas that's stretching, evolving, and hiding mysteries we've only begun to grasp. Time doesn't tick the same everywhere in the universe. In extreme gravity, it stretches like taffy, bending to the will of cosmic monsters. Near a black hole's event horizon, where gravity is so strong even light can't escape, time slows to a crawl. For an observer watching from a safe distance, a clock falling toward the abyss would appear to freeze, its hands moving slower and slower until they stop entirely. But here's the twist: if you were the one holding that clock, you wouldn't notice anything unusual. Your watch would keep ticking normally, while centuries might pass for someone waiting light years away. This isn't science fiction, it's Einstein's theory of general relativity in action, and it's been tested right here on Earth. Take GPS satellites orbiting high above our planet where gravity is slightly weaker. Their clocks run faster than those on the ground by about 45 microseconds per day. If engineers didn't account for this, your navigation would drift off by miles within hours. Now imagine that effect amplified a billionfold near a neutron star, where time slows so dramatically that a single second for you could stretch into years for distant observers. It's as if the universe has built-in speed bumps in space-time, and the most unstable zones, black holes, neutron stars, are where the brakes slam hardest. But time dilation isn't just a curiosity, it's a window into the fabric of reality. In the swirling chaos around a black hole, time and space swap roles. What we perceive as the inevitable march of time becomes just another direction you could move in, like left or right. Cross the event horizon, and the singularity no longer lies ahead of you, it's in your future, as unavoidable as tomorrow. This flip in causality is why black holes are the ultimate time machines, not in the sci-fi sense, but as natural laboratories where the rules of time get rewritten. Could these extreme environments hint at possibilities like time travel? The math gets murky here. Wormholes, hypothetical shortcuts through space-time, might theoretically allow for backward time travel if stabilized by exotic matter with negative energy. But in reality, the radiation and tidal forces near a black hole would shred anything daring to approach such a path. Even if you survived, the universe has a nasty habit of creating paradox-proof mechanisms, like quantum mechanics, ensuring you can't go back and prevent your own birth. Yet the instability of time in these zones still teases us with mysteries. Some theories suggest that inside a rotating black hole, closed time-like curves could form, loops where time circles back on itself. Others propose that the extreme time dilation near neutron stars might allow civilizations to, in essence, fast forward through cosmic history by orbiting close enough to outlive the rest of the universe. These ideas flirt with the edge of known physics, but that's what makes them so tantalizing. What's clear is that time isn't the universal constant we once thought. It's fluid, malleable, and deeply personal, a thread woven into space-time that gravity can stretch, compress, or even not. And in the most unstable corners of the cosmos, where light and gravity wage their endless war, time itself becomes another casualty, or perhaps another weapon in the universe's arsenal of wonders. The moment of cosmic inflation was the universe's most violent identity crisis, a split second when space itself lost all sense of scale, ballooning from smaller than an atom to the size of a galaxy in less time than it takes light to cross a single proton. Picture a runaway explosion where the very fabric of reality expanded faster than the speed of light, not once, not twice, but doubling in size at least 60 times over. This wasn't just rapid growth, it was exponential chaos, stretching quantum ripples into cosmic mountains and valleys that would later become the seeds for everything we see today. Those quantum fluctuations, tiny hiccups in the newborn universe, got frozen into space-time like fingerprints pressed into wet clay. As inflation stretched them, they became the blueprint for all structure. The dense regions collapsing into galaxies, the sparse ones becoming cosmic voids. Without this instability, the universe might have remained a featureless sea of particles, never clumping into stars, planets, or us. But here's the twist: inflation didn't just plant the seeds for galaxies, it also left behind a smoking gun, a faint afterglow we now call the cosmic microwave background. The temperature variations in this ancient light are snapshots of those quantum ripples stretched across the sky like a cosmic fingerprint. Yet inflation's legacy isn't just about the past, it's a clue to the universe's future. Some theories suggest that the same process could happen again, triggered by quantum tunneling or a shift in dark energy's behavior. Imagine a bubble of space suddenly inflating inside our universe, birthing an entirely new cosmos with its own laws of physics. It's a mind-bending thought. Our entire observable universe might just be one bubble in an endless foam of inflationary realms, each with its own unstable zones and cosmic dramas. What makes inflation so hard to study is its sheer extremity. The energy scales involved are trillions of times beyond what any particle collider could recreate, and the evidence is subtle, hidden in the polarization patterns of the cosmic microwave background or the statistical distribution of galaxies. But if we crack its secrets, we wouldn't just understand the Big Bang, we'd glimpse the ultimate unstable zone, where the rules of physics as we know them were forged in fire. And that could rewrite not just cosmology, but our very understanding of reality itself. What if our universe isn't the only one, hidden within the most chaotic corners of space, black holes, cosmic strings, or even the seething quantum foam? There might be doorways to realities beyond our own. The multiverse hypothesis isn't just science fiction. It's a serious scientific idea that emerges from the edges of cosmology and quantum physics. Picture a black hole not as a dead end, but as a bridge. At its core, where gravity crushes matter into infinite density, space-time might pinch into a tunnel, a wormhole threading through higher dimensions to another universe entirely. It's a staggering thought. These cosmic wrecking balls could also be cosmic architects, stitching the fabric of existence into a vast, interconnected web of worlds. But how would such a connection even work? Take cosmic strings, those hypothetical scars from the universe's birth. If they exist, their unimaginable density could warp space-time so severely that they fold it back on itself, creating shortcuts between distant points or even different realities. In some theories, two colliding cosmic strings might twist space-time into a knot so tight it briefly opens a portal to another universe. These wouldn't be stable gateways you could stroll through, more like fleeting cracks in reality, snapping shut as quickly as they form. Yet the mere possibility rewrites what we consider the limits of physics. The wildest part, each of these alternate universes could operate by completely different rules. In one, gravity might be repulsive instead of attractive, flinging stars apart like confetti. In another, light could move at a snail's pace, turning the cosmos into a slow-motion dreamscape. Some might lack dark energy, causing them to collapse back into a big crunch, while others could be so dense with matter that black holes form spontaneously in empty space. The diversity is mind-boggling, and if the multiverse is real, our universe's laws might just be a lucky roll of the dice, one combination in an infinite cosmic lottery. So how do we test something so outlandish? Clues might lurk in the aftermath of black hole collisions. When two singularities merge, the gravitational waves they produce carry subtle imprints of their environment. If those ripples show anomalies, echoes, or frequencies that defy prediction, it could hint at unseen dimensions or even leakage from neighboring universes. Similarly, if cosmic strings exist, their gravitational lensing effects might reveal unnatural twists in spacetime, like a reflection in a funhouse mirror that shouldn't be there. Even the cosmic microwave background, that ancient glow from the Big Bang, could hold patterns suggestive of a collision with another universe long ago. Of course, skepticism is healthy. The multiverse remains untested, and some argue it's not even falsifiable, a criticism that strikes at the heart of the scientific method. But the pursuit isn't just about proving alternate realities exist. It's about probing the extremes of what's possible, asking whether our universe's most unstable zones are glitches in the system or something far more profound. Every time we detect a gravitational wave or map the cosmic microwave background, we're not just studying our universe, we're searching for fingerprints of the impossible. And whether the answer is yes or no, the journey reshapes our understanding of existence itself. What's certain is this: if portals to other worlds do exist, they're hiding in plain sight, woven into the chaos of black holes, the ghostly strands of cosmic strings, or the frothy turbulence of quantum spacetime. The universe has never been shy about revealing its secrets in the unlikeliest places. So why should the multiverse be any different? Quantum entanglement already defies common sense: particles linked across vast distances, instantly mirroring each other's states no matter how far apart they drift. But in the crushing depths of a black hole's event horizon, this phenomenon morphs into something even stranger. Picture a pair of entangled particles, one falling into the abyss while its partner escapes. The particle outside remains part of our universe, humming along, obeying quantum rules, while its twin plunges into a realm where space-time itself frays into chaos. Yet somehow their connection persists, threading through the firewall of the event horizon like a cosmic lifeline. This isn't just theoretical musing. It might hold the key to one of physics' greatest puzzles, the black hole information paradox. The paradox hinges on a simple question: when matter vanishes into a black hole, does the information it carries truly disappear? Quantum mechanics says no, information must always be preserved. But general relativity suggests it's obliterated beyond recovery. Entanglement offers a way out. If particles straddling the horizon remain linked, their quantum states could act as a backup, encoding the lost information into Hawking radiation as the black hole evaporates. It's as if the universe keeps a hidden ledger, scribbling the fate of every atom in entangled ink. Even wilder is the idea that entanglement might knit spacetime itself together. In certain theories, the fabric of reality emerges from a vast network of quantum connections, meaning black holes could be testing grounds for how gravity and quantum mechanics intertwine. When two black holes merge, their event horizons might temporarily form a bridge of entangled particles, a phenomenon called ER equals EPR. This speculative link suggests that wormholes and entanglement are two sides of the same coin, with entangled particles acting as microscopic tunnels through spacetime. The implications are staggering. If entanglement can survive a black hole's wrath, it might enable forms of communication that bypass normal spacetime constraints. Imagine two scientists, one orbiting a black hole while the other watches from afar. By manipulating entangled particles, they could theoretically transmit information faster than light, or at least create the illusion of doing so. Of course, practical hurdles loom large. The energy required would dwarf anything humanity could muster, and decoding the signals would demand technology beyond our wildest dreams. But the mere possibility reshapes how we think about causality and connection in the cosmos. Testing these ideas isn't just about satisfying curiosity, it's about probing the universe's deepest architecture. Labs on Earth are already simulating black hole conditions with ultra-cold atoms and lasers, watching how entanglement behaves under extreme strain. Meanwhile, telescopes scour the skies for anomalies in Hawking radiation analogs, hunting for echoes of quantum links severed by event horizons. Every experiment, every observation, brings us closer to answering whether entanglement is the glue holding reality together, or just one thread in a tapestry we've barely begun to unravel. What's certain is this: in the universe's most unstable zones, the rules we take for granted don't just bend, they shatter. and in their wreckage, we might find the clues to a theory that finally unites quantum weirdness with gravitational might, revealing a cosmos far stranger and far more connected than we ever imagined. The universe should be buzzing with life, with billions of galaxies, each brimming with stars and planets. The sheer numbers suggest we shouldn't be alone, and yet the cosmos remains eerily silent. This is the Fermi paradox, the glaring contradiction between the high probability of alien civilizations and the complete lack of evidence for them. But what if the answer lies in the very unstable zones we've been exploring? These cosmic death traps might not just be extreme environments, they could be the reason the universe feels so empty. Take gamma-ray bursts, for example. These catastrophic explosions flood their surroundings with lethal radiation, sterilizing entire galaxies in seconds. A single burst within a few thousand light-years could wipe out complex life on Earth, leaving behind a radioactive wasteland. If such events are common, they might act as a universal reset button, snuffing out civilizations before they ever get the chance to signal their existence. Even worse, the regions most likely to harbor life-dense star-forming areas are also where gamma-ray bursts occur most frequently. It's like building a house in a hurricane zone and wondering why no one sticks around. Then there are black holes, those gravitational monsters lurking in galactic cores. A wandering black hole passing through a solar system wouldn't just disrupt orbits, it could fling planets into deep space or devour them whole. Supermassive black holes, meanwhile, occasionally go on feeding frenzies, unleashing jets of plasma that cook everything in their path. If advanced civilizations arise near these unstable zones, their survival might hinge on leaving before the neighborhood turns deadly. But here's the twist. What if some civilizations don't just survive these hazards, they exploit them? A species with enough technological prowess might harness the energy of an accretion disk, using a black hole as the ultimate power plant. Or perhaps they've mastered gravitational wave propulsion, riding space-time ripples like a surfer on a cosmic tide. Unstable zones could be the intergalactic equivalent of gold rush towns, dangerous, but full of opportunity for those bold enough to stake a claim. The chilling possibility, though, is that the universe is simply too hostile for life to thrive long-term. Between gamma-ray bursts, black hole mergers, and wandering hypervelocity stars, the cosmos might be a gauntlet where only the luckiest or most resourceful make it through. Or maybe we're the odd ones, evolving in a rare quiet pocket while the rest of the universe burns. Or perhaps the answer is even stranger. What if civilizations that survive long enough don't bother with radio signals or Dyson spheres? Maybe they've transcended into dimensions we can't perceive, or they've encoded their existence into the fabric of spacetime itself, leaving traces only detectable through gravitational waves or quantum entanglement. The truth might not be that the universe is empty, just that we're still learning how to listen. One thing's certain, unstable zones aren't just cosmic curiosities. They're the gatekeepers of life's potential, the silent architects of the universe's grand narrative. And as we peer deeper into the chaos, we're not just searching for answers about alien life, we're uncovering the rules of survival in a cosmos that's far less hospitable than we ever imagined. Simulating the universe's most extreme environments here on Earth sounds like science fiction, but it's happening right now in labs around the world. Scientists can't pack their bags for a trip to a black hole, so they've done the next best thing. They've recreated microscopic slices of cosmic chaos using some of the most advanced technology ever built. At facilities like the National Ignition Facility in California or the Large Hadron Collider in Switzerland, lasers powerful enough to vaporize diamonds and particle beams moving at nearly light speed are standing in for neutron stars and black holes, letting us test theories without waiting for a cosmic catastrophe. One of the most groundbreaking simulations involves creating artificial event horizons, the point of no return around a black hole. Using specially designed fiber optics or even flowing water, researchers have found ways to mimic how light behaves when it's trapped by extreme gravity. In these experiments, laser pulses act like photons trying to escape, while the simulated horizon drags them backward, just as they would near a real black hole. The result, light doesn't just slow down, it gets stretched and twisted in eerie ways, matching predictions from Einstein's equations. These tabletop black holes can't crush matter into oblivion, but they've already confirmed subtle effects like Hawking radiation, the faint glow theorized to leak from real black holes over eons. Then there's the matter of neutron stars. Their crushing gravity, so intense it squeezes atoms into a soup of pure neutrons, is impossible to replicate directly. But scientists have found workarounds. By smashing heavy ions together at nearly light speed in particle colliders, they've created quark-gluon plasma, a state of matter that hasn't existed freely since the universe's first microseconds. This super-hot, super-dense soup behaves strikingly like the interior of a neutron star, offering clues about how matter acts under pressures that would flatten Earth into a pancake. Some experiments even suggest strange new phases of matter might exist in these conditions, like nuclear pasta, a structure so dense they form shapes resembling spaghetti or lasagna sheets deep inside neutron stars. But the real magic happens when simulations collide with theory. Take magnetars, those ultramagnetic neutron stars. Labs can't recreate fields trillions of times stronger than Earth's, but by studying how plasma behaves in high-field experiments, physicists have uncovered hints about how magnetar flares launch. Similarly, gamma-ray bursts, the universe's most powerful explosions, are being probed using laser-driven shockwaves that mimic the relativistic jets piercing dying stars. Each experiment is like a puzzle piece, helping us assemble a picture of physics under conditions we'd otherwise never witness firsthand. The future of these simulations is even wilder. Next-generation lasers, like those planned for the extreme light infrastructure, will reach intensities where light itself breaks down into matter and antimatter pairs, conditions near what theorists predict exist just outside black hole horizons. Quantum simulators, using ultra-cold atoms to model spacetime curvature, might one day let us test ideas about wormholes or quantum gravity. And as computing power grows, virtual black holes modeled in supercomputers are becoming so detailed they can track individual particles spiraling into oblivion. What's astonishing isn't just the tech, it's how much we've learned without leaving our planet. These experiments have already reshaped our understanding of event horizons, neutron star cores, and even the birth of the universe itself. And with every breakthrough, we're not just simulating cosmic chaos, we're bringing the universe's most unstable zones into the lab, one laser pulse at a time. We're standing on the brink of a new era in cosmic exploration, one where the universe's most unstable zones are no longer hidden in shadow. With tools like the James Webb Space Telescope, we're not just observing these chaotic frontiers, we're dissecting them in unprecedented detail. Webb's infrared eyes cut through cosmic dust like a scalpel, revealing the violent births of stars in stellar nurseries and the frenzied orbits of matter around supermassive black holes. Already, it's spotted galaxies so ancient their light has been stretched and twisted by gravitational lensing, offering a backstage pass to the cosmic dramas unfolding in the early universe. But the real revolution isn't just in seeing deeper, it's in hearing the universe's hidden symphony through gravitational waves. Detectors like LIGO and Virgo have turned space-time ripples into a new language for decoding cosmic collisions. Future upgrades will make these instruments even more sensitive, catching whispers from black hole mergers so distant they predate the formation of our solar system. Imagine tuning into the faint echoes of neutron stars spiraling together 10 billion years ago, or detecting the tremors of primordial black holes, relics from the universe's first second crashing into one another. These waves aren't just signals, they're time machines carrying stories from epochs when the cosmos was a far wilder place, and the next generation of missions. They're poised to push boundaries we've only dreamed of. The European Space Agency's LISA project, a trio of spacecraft set to launch in the 2030s, will float in formation 1 million miles apart, forming a gravitational wave observatory so vast it could detect mergers between supermassive black holes anywhere in the observable universe. Closer to home, NASA's proposed interstellar probe might venture beyond our solar system, carrying instruments to study the turbulent magnetic fields and particle storms near neutron stars, regions where the very fabric of matter is stretched to its limits. But the most tantalizing frontier lies in testing quantum gravity itself. Experiments like the Event Horizon Telescope, which captured the first image of a black hole's shadow, are now turning their gaze to Sagittarius A star, the supermassive black hole at our galaxy's core. By watching how light flickers and bends at the event horizon, scientists hope to spot deviations from Einstein's predictions, hints of quantum effects warping spacetime on microscopic scales. Other projects aim to recreate black hole conditions in labs using ultra-cold quantum fluids or high-energy lasers, probing how information might escape these cosmic traps. What makes this moment so electrifying isn't just the technology, it's the sheer unpredictability of what we might find. Every time we've pointed a new tool at the cosmos, it's upended our assumptions. Gravitational waves revealed black holes far heavier than anyone expected. Webb's deep field images showed galaxies too mature for their age, forcing us to rethink cosmic evolution. The next breakthrough could be anything: evidence of wormholes, signs of extra dimensions, or even a crack in the foundation of relativity itself. The unstable zones we're exploring aren't just cosmic oddities, they're the universe's way of stress testing its own rules. And as we peer deeper into their chaos, we're not just solving puzzles, we're rewriting the story of how reality works. The tools are ready, the questions are waiting. All that's left is to listen, watch, and discover. The fate of the universe isn't written in the calm, predictable regions of space. It's being decided right now in the most unstable zones where chaos reigns supreme. Picture a cosmic tug of war between titanic forces, black holes slowly evaporating into Hawking radiation, dark energy relentlessly stretching space-time, and gravitational behemoths locked in endless collisions. Each of these violent processes isn't just a spectacle, it's a vote being cast in the ultimate election, determining whether reality ends in fire, ice, or something far stranger. Consider the slow death of black holes first. These gravitational monsters might seem eternal, but quantum mechanics paints a different picture. Over timescales so vast they make the current age of the universe look like a blink. Even the largest black holes will radiate away their mass, fading into nothingness with a final burst of particles. But here's the twist: this process could rewrite the cosmos expiration date. As black holes vanish, they might leave behind a cold, dark universe where matter is so thinly spread that new stars can never form again. We'd be left with a graveyard of dead stars and planets, drifting farther and farther apart as dark energy pushes them into eternal exile. Then there's dark energy's terrifying potential, not just to expand space but to shred it. If its strength increases over time rather than remaining constant, we could face the Big Rip, a scenario where first galaxies, then solar systems, and eventually atoms themselves are torn apart by the runaway expansion of space. Imagine looking up one day to see the moon suddenly disappear, not because it moved, but because the space between Earth and its satellite stretched faster than light could bridge the gap. It's an ending so violent it makes supernova look gentle by comparison. But gravity hasn't surrendered yet. Some theories suggest that dark energy might weaken over time, allowing gravity to regain control in a dramatic reversal. This could lead to the Big Crunch, a mirror image of the Big Bang where everything collapses back into a singularity. Galaxies would rush toward each other, temperatures would soar, and eventually all matter would be compressed into an ultra-hot, ultra-dense point. Some models even propose this singularity might trigger a new Big Bang, birthing another universe in an endless cycle of cosmic rebirth, the wild card in all this. Unstable zones we haven't discovered yet. Just as quantum foam and cosmic strings were once pure theory before entering mainstream cosmology, there could be other space-time defects or exotic phenomena lurking in the cosmic shadows, waiting to rewrite our predictions. Some speculative models suggest bubbles of false vacuum decay might appear spontaneously, expanding at light speed to rewrite the fundamental laws of physics in their wake. Others propose that colliding brains in higher dimensions could reset the universe like a cosmic etch-a-sketch. What makes studying these extreme environments so crucial is that they're not just destructive, they're creative. The same processes that could end the universe also built it. Every black hole's death throes might seed new particles. Every cosmic collision could forge unexpected structures. Even in the bleakest scenarios, there's potential for something new to emerge from the chaos. The universe's finale might not be an ending at all, but a transformation we can scarcely imagine. One where today's unstable zones become tomorrow's building blocks for realities beyond our current comprehension. Imagine a civilization advanced enough to siphon energy from a black hole's accretion disk, or to stabilize a wormhole for near-instant travel across the galaxy. The possibilities sound like science fiction, but with rapid advancements in physics and engineering, these scenarios edge closer to reality. The real question isn't just whether we can tamper with the universe's most unstable zones, it's whether we should. Tinkering with cosmic forces we barely understand isn't like flipping a switch in a lab. It's more like performing heart surgery with a sledgehammer. One misstep could unravel the delicate balance holding entire star systems together, or worse, trigger chain reactions with consequences spanning light years. Take black hole energy extraction, for instance. Theoretically, we could harness the intense radiation from an accretion disk or even exploit the Penrose process, stealing rotational energy from a spinning black hole. But what happens if we destabilize the disk? A sudden release of trapped energy could flood nearby space with lethal radiation, sterilizing planets we never knew existed. Or consider artificial unstable zones, like creating microscopic black holes in particle colliders to study quantum gravity. The risk of one growing uncontrollably is vanishingly small, but not zero. The stakes: swallowing Earth into a singularity the size of an atom. Then there's the ethical weight of unintended consequences. Unstable zones aren't isolated phenomena, they're woven into the cosmic web. A black hole's gravity shapes the orbits of stars around it. Neutron star collisions seed galaxies with heavy elements. If we alter one piece of this puzzle, could we inadvertently rewrite the life cycle of entire galaxies? Imagine a future where humanity becomes the careless child in the cosmic china shop, shattering systems that took billions of years to form. Yet the temptation is undeniable. The energy locked in these violent realms could power civilizations for eons. Mastering space-time defects might let us traverse the universe or even manipulate time itself. But with such power comes profound responsibility and a chilling precedent. If one civilization can reshape unstable zones, what stops others from weaponizing them? A black hole's gravity could fling stars like bullets. A triggered gamma-ray burst might erase life across whole sectors of space. The same tools that elevate us could become instruments of cosmic-scale destruction. Perhaps the most unsettling thought is this: some unstable zones might exist for a reason. They could be nature's pressure valves, regulating galactic evolution or preserving quantum balances we don't yet comprehend. Interfering might not just be risky, it could blind us to truths hidden in their chaos. Before we reach for these levers, we need more than curiosity and ambition. We need humility to recognize that some frontiers aren't meant to be conquered, only studied from a safe distance. The universe has operated just fine without our meddling for 13.8 billion years. Maybe for now, observation should be our only intervention. Hollywood has turned black holes into cosmic vacuum cleaners, swirling vortexes that suck in everything in sight with dramatic sound effects. But the reality is far stranger and more fascinating. Real black holes don't actually suck matter in like a Hollywood special effect. Instead, their immense gravity bends spacetime so severely that objects simply follow the curve, like a marble spiraling around a funnel. If our sun were magically replaced by a black hole of the same mass, Earth's orbit wouldn't change at all. The danger isn't some indiscriminate cosmic hoovering. It's the tidal forces that would stretch you like taffy long before you reach the event horizon. Then there's the myth of wormholes as convenient interstellar highways, ready for starships to zip through. Movies love showing these tunnels as shimmering, stable gateways, but the truth is far less glamorous. Even if wormholes exist, they'd likely collapse instantly unless propped open by exotic matter with negative energy, something we've never observed. And forget steering through one without being shredded by intense gravitational shear or cooked by radiation. The closest thing to a safe wormhole in nature might be the fleeting quantum foam fluctuations at scales a trillion times smaller than an atom, snapping shut before even a single photon could slip through. Pop culture also loves portraying neutron stars as merely dense, inert relics, cosmic paperweights. In reality, these stellar corpses are anything but quiet. A teaspoon of neutron star material weighs as much as a mountain, yes, but they're also spinning faster than blender blades, some completing hundreds of rotations every second. Their magnetic fields are so intense they could erase credit card data from halfway across the solar system. And when two neutron stars collide, that's not just a flashy explosion. It's the universe's primary forge for gold, platinum, and other heavy elements. Your wedding ring might owe its existence to a cataclysmic merger billions of years ago. Even dark energy gets misrepresented as some ominous force, pulling the universe apart. In truth, it's not pulling at all. It's the very fabric of space itself expanding, carrying galaxies along like raisins in rising bread dough. This expansion isn't tearing solar systems or atoms apart yet because gravity and other forces still hold them together. The real mystery isn't some malevolent energy, but why this expansion is accelerating at all. Clearing up these misconceptions matters because these cosmic extremes aren't just abstract curiosities. They're laboratories for the universe's most fundamental laws. When we mistake black holes for sci-fi plot devices, we overlook their real role as time capsules of gravity's secrets. When we simplify neutron stars into mere dead stars, we ignore the quantum marvels happening in their cores. And when we treat dark energy as a villain, we miss the chance to ask why the cosmos behaves this way in the first place. The beauty of these unstable zones isn't in their Hollywood theatrics, it's in how they force us to rethink reality. A black hole's event horizon isn't just a boundary, It's a firewall for physics where Einstein's relativity crashes into quantum mechanics. A gamma-ray burst isn't just a flashy explosion. It's a messenger from the early universe, carrying clues about star formation billions of years ago. Understanding them doesn't require a PhD, just the willingness to look beyond the myths and embrace the universe's true, breathtaking chaos. After all, the real story is stranger and far more thrilling than anything a screenwriter could invent. Unsolved mysteries lurk in every corner of the universe's most unstable zones, defying even our boldest scientific theories. Take black holes. We've mapped their edges with groundbreaking images of event horizons. But what lies beyond that point of no return remains one of physics' greatest enigmas. The equations suggest a singularity, a point of infinite density where spacetime itself breaks down. But infinities don't sit well with physicists. They're often a sign that our theories are incomplete. Could the core of a black hole be a portal to another universe, as some models suggest? Or does quantum gravity step in to prevent the singularity, replacing it with something even stranger, like a dense knot of spacetime foam? Right now, we're like detectives peering through a keyhole, catching only glimpses of a room we can't yet enter. Then there's the puzzle of white holes, the hypothetical twins of black holes, spewing matter outward instead of drawing it in. Einstein's math allows for them, but nature seems to have skipped this chapter. No one has ever detected a white hole's telltale outburst of energy, leaving scientists divided. Some argue they're mathematical curiosities with no real-world counterpart, while others speculate they could be hiding in plain sight, masquerading as bizarre gamma-ray bursts or even the Big Bang itself. Imagine uncovering one, a cosmic geyser erupting with particles that somehow remember being crushed in a black hole's grip. It's the kind of discovery that would rewrite textbooks overnight. Magnetars add another layer of bewilderment. These neutron stars generate magnetic fields so powerful they could strip atoms apart from thousands of miles away. But how? The leading theory points to their mind-bendingly dense cores, where protons and electrons merge into a sea of neutrons swirling at near light speeds. This chaotic dance might amplify magnetic fields to ludicrous strengths, like a cosmic dynamo gone haywire. Yet even this explanation feels incomplete. Some magnetars exhibit sudden, violent eruption starquakes that release more energy in a millisecond than our sun does in 100,000 years. What triggers these outbursts? Is it the snapping of magnetic field lines or something deeper, tied to quantum quirks in the star's core? Every flare we observe sends theorists back to their chalkboards, searching for clues in the chaos. Even the seemingly straightforward isn't safe from mystery. Take gamma-ray bursts. We've linked some to collapsing stars and neutron-star collisions, but others defy categorization. Why do a handful of these explosions outshine entire galaxies for seconds or sometimes minutes with no obvious cause? And what about fast radio bursts, those split-second cosmic chirps that zip across the universe? Some repeat predictably, others vanish without a trace. Are they the screams of magnetars, the collisions of exotic stars, or dare we speculate something even more exotic? The beauty of these unanswered questions isn't just in their complexity, it's in how they reveal science as a living, evolving pursuit. Every time we think we've pinned down the rules, the universe throws a curveball. A black hole's shadow might flicker in ways Einstein never predicted. A magnetar's flare might hint at states of matter that don't exist on Earth. These unstable zones aren't just cosmic oddities, they're the universe's way of nudging us toward deeper truths. And that's what makes them irresistible. They're not just destroying the old rules, they're inviting us to invent new ones. From black holes to neutron star collisions, these cosmic battlegrounds are nature's ultimate testing grounds, places where the laws of physics are pushed to their breaking point. Imagine standing at the edge of a black hole's event horizon, where gravity twists light into impossible shapes, or witnessing two neutron stars slam together with enough force to forge gold in an instant. These aren't just distant spectacles, they're active experiments unfolding in real time, revealing clues about how matter, energy, and space-time itself behave under conditions we could never recreate on Earth. What makes these unstable zones so extraordinary isn't just their violence, it's their creativity. Black holes don't just destroy, they transform, warping space-time into knots that might hide wormholes or even gateways to other dimensions. Neutron star collisions don't just explode, they're cosmic alchemists producing elements essential for planets and life. Even the vacuum of space, seething with quantum foam, hints at a hidden turbulence beneath the calm surface of reality. Every extreme environment is a puzzle box packed with secrets waiting to be cracked open, and the tools we're building to study them are just as revolutionary as the phenomena themselves. Gravitational wave detectors act as cosmic stethoscopes, letting us hear the collisions of black holes billions of light years away. Telescopes like James Webb peer into the hearts of galaxies, capturing the glow of quasars that outshine entire star systems. In labs, we're simulating the crushing densities of neutron stars and the warped physics of event horizons, bringing the universe's most hostile landscapes down to Earth. But for all we've learned, the biggest breakthroughs are still ahead. What happens inside a singularity? Could dark energies' grip on the cosmos suddenly tighten, accelerating the universe toward a big rip? Are there other, even stranger, unstable zones lurking beyond our current theories? The answers won't just satisfy curiosity, they'll redefine our place in the cosmos. Every discovery in these chaotic frontiers reminds us that the universe is far wilder, far more inventive than we ever imagined. So the next time you gaze up at the night sky, remember, those quiet stars and distant galaxies are just the serene surface of a much deeper story. Beneath the calm, the universe is a seething arena of creation and destruction, where light and gravity wage an endless war, and we're only beginning to understand the rules. The adventure isn't just out there, it's unfolding in real time, waiting for us to piece together the clues. And one thing's certain, the cosmos will keep surprising us, one unstable zone